I am going to talk to you about something a little different. So it definitely falls into the category of weird things that I have built. So I hope that you enjoy it. So as just mentioned, my name is Sophie. I am an engineer at Incident.io. So we're a small startup based in London, and we do incident management software. So we help companies manage and respond to incidents directly from Slack. As everyone else, we are hiring, so do come find me afterwards if you want to chat. But that is not why I'm here. So in my other life, I'm also a hobbyist musician, and I run a choir as well. And yeah, that's my website, localghost.dev. Sorry, Jess. And my Twitter account is type__error, because one underscore was taken. Rude. So this is my virtual piano. I'm going to talk to you a bit about how I built it. I'm going to share some of the musical theory that went into it. And I'm also going to talk about the API that powers it, which is the Web Audio API. But first, let's see what it does. Directly, you can play some scales. And you can make it play some chords as well. It sounds beautiful. I'm just like Mozart. So how did this come about? Well, in the choir that I mentioned, we have a retreat every year. So we go away for the weekend, we do workshops and we sing, and it's great. For obvious reasons, we couldn't go away last year, so we decided to have a virtual retreat. And I was going to run a workshop on music theory. And I wanted to make it in some way interactive. You can't sing over Zoom, it just doesn't work. So I thought, being a web engineer, I thought, how can I do something interactive so that the people in the workshop can test out what they've learned? And I also saw a really good opportunity here for procrastination. So I managed to put off doing the workshop for as long as I could by building this little virtual piano. So let's start with a bit of musical theory. Apologies to everyone who thought this was a JavaScript conference. But what I find really interesting is that a lot of the musical theory from the workshop actually went into this app. So it helps to go over some of the background there. So sound is made up of vibrations that travel as waves, and we measure that in frequency, which is the number of those vibrations in a given time period. We measure frequency in hertz, which is 1 vibration cycle per second. And if you think of a piano, when you hit the notes on a piano, what's actually happening is there are hammers inside the piano that are hitting strings. And each string for each note has a different thickness and a different length that make it vibrate at a particular frequency so that it makes the right note. And in Western music, we've got a set of 12 tones that we use that have specific frequencies. So we give them a letter, A to G, and those are the seven of the notes, and then the ones in the middle, we call them accidentals. So those are notes which don't really have enough, there's not enough distinction between those and the ones that come either side of them. So we refer to them in terms of how they relate to the notes either side of them. So those black notes are those accidentals, and we just give them a symbol instead of a letter of their own. So for example, an accidental that's one up from A is A sharp, but the one that's one down from B is B flat. And they are the same note, so each accidental has 2 names. And that division of notes is based on the frequency of the note. And the distance between any note and its nearest neighbor is called a semitone. And then 2 semitones together is called a tone. So A to A sharp, that's a semitone, but A to B, that's a whole tone. So on a keyboard has 61 notes. A full-size piano has 88. But on a keyboard, we start from C, and we go all the way up. This is obviously not a full-size keyboard because it's not 61 notes. But the groups of letters repeat. So we go from C to B to C to B to C to B, going from lowest on the left to highest on the right. And those groups of repeating notes, we call them octaves. So on a full-size piano, there's 7 1/4 octaves. And we give them numbers as well. So when we're talking about notes from a kind of theoretical point of view or a scientific point of view, we'll refer to them with their note letter and their number, referring to which octave they belong to. So the one in the middle is octave 4. So a note in that octave might be C4, A4. So this is A4 and A5. It's A in the 4th octave and A in the 5th octave. And it's a weird quirk of our brain that we can hear those notes and kind of just tell they're the same note, but also different. So that one's higher and one's lower, but they are the same note. And that's because each octave jump doubles the frequency. So it's still kind of a very tightly related frequency. It's exactly double. Now, music tends to use some notes, but not all of them. And in Western music, we have sets of 7 notes that you can play to reach the next note in an octave. And that's what we call a scale. If you think of scales like kind of like color palettes that are predefined that will make your music sound a certain way or evoke a certain emotion. And like the most commonly known scale is probably the major scale, which typically invokes happy emotions. So this is the C major scale. It's just the white notes on the piano starting from C, basically. And we can play 7 notes up from C to reach the next C. And the important thing to note about scales is that they follow certain patterns. And being programmers, we love patterns. So this will come in very useful. This is a pattern for the major scale. So here I've shown you G major. And the pattern that we can use and apply to any note on the piano to get the major scale for that note is tone, tone, semitone, tone, 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 semitone. Which means if I start at G and go up a tone to A, then I go up another tone to B, then I go a semitone up to C, another tone, D, another tone, E, another tone, F sharp, and then a semitone to G. And that pattern will give us every single major scale. Cool, code now. So enough musical theory. Let's have a quick look at the Web Audio API. So I'm not going to go into detail about the various different use cases. It's very cool. It lives in your browser. So if you use one of the big 4 browsers, it's all there for you. You can do things like play audio. You can do some very cool Winamp style visualizations. You can analyze audio that's playing. But you can also synthesize audio, and that's what I've done. So looking at those sound waves that we learned about before, what synthesizers do is they generate these waves electronically to make sound. And that's what we need to do, but not electronically, I mean, sort of electronically, but we need to do it with code. We're going to build a little synthesizer. So what we need is an oscillator, which is the thing that makes the waveform that makes sound. We need to actually define what that waveform is going to look like. And then we need to know the frequencies of all the notes on the piano to be able to tell the oscillator what sound to play. And finally, we need a user interface that we can interact with to actually play the piano. So starting out, to actually get access to the Web Audio API, there's an audio context interface that exists on the window object in the browser. It's all native, and we initialize that. For this purpose, we only want one, because if we had more than one, we might end up with lots of things happening at once, which we don't want. And then we call the create oscillator function, and this gives us an oscillator. And in real life, an oscillator is a circuit that produces a constant waveform. But well, I don't know how it works. It's just there. But what we do is we connect it to what's called the audio context destination, which defaults to your system output. So speakers, headphones, that kind of thing. It won't be doing anything just yet. That is loud. So waveforms can take many different shapes. So we need to create the waveform, and the way that we create it is going to determine what the synthesizer sounds like. And there are 4 common waveform patterns, which are sine, square, triangle, and sawtooth. And those waveforms that I just played were sine and square, and they do sound different in the way that they come across. If you think about piano sounds, like often with virtual instruments, they'll actually use samples of real pianos to make the notes for the piano, because it's very difficult to get a realistic sound from an electronic waveform. I didn't try to go for the realistic sound. This is what a waveform looks like in terms of the Web Audio API. So it's like arrays of floats. And those are the plots of the points on those graphs that form a waveform. And we can pass those floats into the create periodic wave function on the audio context, and that will give us a wave that we can then plug into the oscillator. And in this case, I found one on GitHub that someone else had created. So we can set the periodic wave on the oscillator and then start it. And at this point, it's just playing a constant tone. So if we want to play different sounds, how do we go about finding the different tones to play? Well, we can actually calculate them using a formula. And so as long as we know the frequency of one note, we can find the frequency of all the other notes on the piano. Now, A4, which I mentioned before, is a very important note. And it's so important that it's actually standardized as ISO 16 as an orchestral tuning note. And it's got a frequency of 440 hertz, which is a really nice round number. And it's A in the 4th octave. And so if we use this as our kind of anchor, our constant, then we can work out where other notes are in relation to A4, and then work out the frequency. So the function to calculate the note's frequency is based on the position in relation to A4. So the actual function itself is 440, which is the frequency of A4, multiplied by 2 to the power of n over 12, where n is the number of semitones between A4 and our note. So for example, with C5, which is C in the 5th octave on the piano, that's actually, if you count it out on the actual piano, it's 3 notes above. So if we wanted to find the frequency of C5, we'd actually have 440 multiplied by 2 to the power of 3 over 12. And this is how I translated it to code. So the function takes a letter and a number corresponding to the letter of the note and the number of the octave of the target note, and it gives us a frequency. So we need to get the interval between A and our note as if they were in the same octave. And then we get the number of semitones between the octave that we're looking for and octave 4, where A4 lives. And then we add those together. And that gives us the semitone interval between A4 and the note that we're looking for. And then we plug it into the function. So A4 multiplied by math.pow, which is 2 to the power of steps divided by 12. And that gives us a number which we round to 1 decimal point for convenience. And the nice thing about this function is I could then make arrays, which I iterated through and generated just all of the notes on the keyboard, which was very convenient for what came next. So the next step is to build a piano interface. And I did this in React. Vanilla JavaScript would have worked just as well. I used a library called Piano SVG, which is an open source thing that someone built to render a piano in SVG, which is very convenient. So I ported that over, and each key is its own component, and it has an ID. And so I have an array of notes and an array of keys, and the index of each note in the array corresponds to a key on the piano. So a key with the ID 2 will play the second note in the array, or the third note in the array. What kind of programmer am I? And the piano lives inside a player component, which controls all the functions and the logic of actually playing the sounds. So it's got all the things like the oscillators and all of that stuff. And there's a sustain pedal, which allows you to hold notes down. So when I showed you the demo before, playing the chords, we have a sustain pedal, which will then mean that when we press one note and we press another note, they'll both keep playing. And when playing a note, we set the frequency of an oscillator. An oscillator can play one note at a time. So there's 2 kind of different modes that we're doing here. There's with the sustain pedal off, you'd set the frequency of the oscillator to a particular note when you click a key. But with the pedal on, you'd actually create a new oscillator for every key that you press, so that you can have multiple sounds at once. Turns out that it's kind of a mess. I had a lot of problems with this. If you play with it now, which you absolutely can, you'll see a little disclaimer at the bottom that says if the notes get stuck, just refresh the page, which is my solution to the fact that sometimes the notes just don't stop. So even though I stop the oscillators and I disconnect them and all sorts of things, sometimes it just doesn't work. I'm not sure whether that's something I did or whether it's a problem with the API. And I also found that they were very slow to initialize. So you need to initialize an oscillator before you can do anything to it. And it's not an async function, but I ended up having to wrap it in a promise because sometimes you would initialize the oscillator and then just try and perform something on it and it would still be undefined. So yeah, a few teething problems. So when it comes to playing scales, we remember that scales are essentially, at their core, patterns. And we can translate those to code through numbers. So a tone, if you remember tones and semitones, a tone is 2 semitones. And the pattern for the major scale was tone, 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 semitone, tone, tone, semitone, tone, 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 semitone. If we translate that to numbers, we get 2, 2, 1, 2, 2, 2, 1. And if 0 is our root note, we can then iterate through that array to find the next note at that position. And so, so I had a table of scales, like a map of scales, all the different scales I could think of with their various patterns. And then when you select a scale on the UI, then it calculates the notes into an array and then plays them. So that is calculating the note pattern. So we kind of have a cursor, and then we iterate through the pattern, and then the cursor moves depending on which note in the array we're on. So when it comes to playing the scale, again, we have one oscillator because we want to play one note at a time, and we want to change the frequency of the oscillator in a regular interval. So I use timeouts, and I set the timeout to ½ a second multiplied by the index of that note in the array. So every note in the array gets a timeout. And when that timeout elapses, the frequency of the oscillator is set to that note. And I store all of these timeouts in component state so that if we wanted to press stop, we could cancel all the timeouts and stop playback. And for chords, it's very similar. There's fewer notes in chords, but they still follow predictable patterns. So if you play a major chord, there will be like a first, a third, and a fifth, basically. So 1, 3, 5 in a scale. And so unlike with scales, we want to play all of the notes at once. So for each note in the chord, we create a new oscillator and set the frequency to that note. And that is basically it. So you can have a play yourself. It's at virtualpiano.vercel.app. All sorts of different scales and chords to play with there. And you can also see the source code at github.com/Sophie Koonin/virtualpiano. And that is me. You can find me afterwards. I'll be floating around, or send me a message on Twitter, or leave something on Veto as well. Thank you very much.